probably can't play tonight. I gotta give a briefing tomorrow. Get started. Yeah. Also didn't do a whole lot this weekend. Okay. All right, I got you. Thank you. See you later. Ciao.
Hamilton still at 14.4. Result 14.4. You were 300. And Max.
All right, those people online, can you hear us? Can you see the graph very much? Say something. Looks like doesn't.
Yes.
Okay.
Yeah, I can.
I can hear you. Okay. Julian, say something. Can you hear me?
Yeah.
Okay. Great. I hope you're not sick. Oh, it's all right. Don't worry. Okay, so basically I'm going to mute your microphone, okay, to begin with. So if you have any question, just unmute and start talking. And then everybody in the classroom will hear you, okay? You got that? Hello? Okay. Anyways, I know you're listening. It's easy to fall in sleep online and nobody knows, and it's okay, but it's okay, but it's up to you. It's your education, not mine. I just teach. If I don't run it, it's not my problem. Okay, it's all up to you. Okay, so let me just start doing today's lecture. I'm going to share my desktop. Okay, and I'm gonna go ahead and start doing that. By the way, I changed my wallpaper, as you can see. Because you have to probably do your best to minimize your stress, Oh my. Okay, so we're going to start unit actually today. And then we're going to start with announcement.
Yes.
Lots of announcement, of course. So I hope you just basically keep it up. Oh, wait a minute, it's 1 o'clock. I forgot to take away your some kind of thing. Today is something to do, right?
Yeah.
See, I cannot even catch up. Today is like what, Monday? Monday before noon, unit A1 homework assignment to do. I forgot to take it before I show up here, so powerful is still up there. Okay. So occasionally the teacher forgets take advantage of it because it's all my fault. Or you can, right? You can still see the file folder, I guess, from your side, right? Because I really forgot to take it. If you want to remind me, you can just go ahead and send the Microsoft Teams text and say, hey, Dr. H, you haven't taken my file folder yet. Are you going to take it? Oh, thank you very much. I start taking it. Or you can pretend like, oh, he forgets. Let's just do something. Anyway, let's just take the attendance. Ready to go? Do you have a paper? Do you have a paper? Do you have a paper? If you don't have it, raise your hand now. Do you have a paper? Okay, let's just get going. All right. Dấu nhiên sẽ tiếng Anh cover ID answer this one. Yeah. Either after me, we can
paper one specifically, or just $2 days now. It's very nice.
Did I go through UKF by the way? I thought I went through. Did I skip you?
No, you
Okay, I went through that. Okay, that's what you said. Looking good. Done. So let's just go over the announcement. Make sure you don't forget something like I already forgot this one. I forgot to take the file out. The file's still up. Too bad. Sorry. Occasionally I do, not always. But there are so many things to do, so I cannot keep it up unless I look at my own announcement. And then today's, of course, you have done, but you worked on homework of Unit A1, you're all done. You submitted, right? I hope so. So A1 is done. It's in the past. You mastered A1, that means units. What is the huge subject in Unit A1? Units. Now you know the difference between pound mass and pound force, and you know why you have to differentiate those two. Now you know the difference between kilogram mass and kilogram force. Now you know why you have to differentiate those two. Important things. Without it, you cannot call yourself aerospace engineer, period. Okay? So I hope you mastered it. Now if you say, oh, I'm not sure, hey, talk to me. Don't ignore it. I know some of you are completely ignoring me. It's your decision if you keep doing that. If you screwed up quiz 1, talk to me. Okay? Important. So now everything is posted. In other words, solutions page. If you click here, well, quiz 0 answer key is here, of course. This is answer key, not the solution. Of course, I'm not going to give you a solution. You're going to figure out all the solution by yourself. But I started to kind of release, this is quiz 0 problem 1A, this is quiz 0 problem 1B, this is quiz 1A, this is quiz 1B. Those are the solutions. You can take a look at it. Of course, you can see this is a solution done by software, something called MathCAD. MathCAD is going to auto-convert all the units. So it's impossible for me to make a mistake. So those are the numbers I got. I can guarantee almost, but I'm human. I may make mistakes, but I'm done with software. So this is probably more accurate than anybody in this classroom. Okay, so please double check the process by yourself. Solution is posted now. Okay. Okay, so far. So unit A1 is over. That means I expect you mastering all the skills of units. If not, talk to me. I mean it. Okay. Things become too late very quickly in this class. Now, if the things becomes too late, I'll probably stop talking to you because it's too late. Okay, so as long as you are receiving those emails, very pesky emails saying, hey, come see me, you're doing something wrong, you're not passing right now. As long as you're receiving those emails, there's a hope. As long as you want to fix it. Now, I'm going to stop sending those things. If I start feeding, hey, this is too late, that's it, sorry. Okay, so take it seriously, please. Some of you, okay? So where am I? Ooh, so today's Monday, right? So something coming up on Wednesday. Obviously, what? Wednesdays, what? Wednesday, noon, September 15, quiz 2. That's 2. So before you do quiz 2, obviously you have to finish up quiz 0 program 2. Figure it out by yourself without doing it. There's no meaning of doing quiz 2. Step by step process. Make sure you figure out quiz 0 program 2. Okay. Then and only then, do your quiz 2 and submit before noon Wednesday. Okay. Next thing up, obviously after you complete unit A1, complete quiz 0 program 2, complete quiz 2, then and only then you're ready to go for unit A2. Unit A2 is all YouTube. I'm not going to do lecture here in this classroom. However, if you have any specific question in lecture A2, please feel free to ask that kind of question. I'll be happy to spend some time going over it. No problem. But I'm not going to do lecture of unit A2. Everything is YouTube. Okay? And then, well, by Friday, I guess you're done. So please submit your homework of A2 Friday. You can negotiate. Of course, somebody starts screaming, hey, Professor, you're insane. We can't do that. Push it back, damn it, kind of thing. If everybody else go like, oh, yeah, let's do it, it's negotiable. But suppose if that's the only one person, I'm not going to listen. So it's up to you. If everybody starts screaming, yeah, it's negotiable, but if you are the only one, you are left behind. Do you understand? So there's a room to negotiate, but don't expect too much. Don't count on it. Just do your best. After doing everything you can screaming and trying to negotiate, fine, I'll be listening. But right now, I think you can finish up by Friday. That's my feeling. Or am I overestimating you? I don't know. Please do your best. Okay? Step by step. In other words, do not go jump right in doing Unit A2 homework assignment without doing quiz 2 and stuff. That's stupid if you do such a thing. Don't do that. Step by step, okay? Any questions so far? So those are all the announcements, and then those are actually updates. Those are just a handout kind of thing, extra information I'm going to refer to as I move on in Unit A3. So today, we're going to start Unit A3. Are you ready to go? I hope so. So here's one thing. I kind of noticed that lots of people don't bring the lecture notes to the classroom. I mean, lots of people actually bring a piece of paper, showing up in classroom, and then writing down something. What are you writing down? My question is, are you really understanding the classroom lecture? I mean, bring the notes. Print it out. Go to library. Print everything in color or something. Print out 200, how many pages? I don't know. I'm not sure.
16.
Maybe 16 for one unit. 4 days. So total for the entire semester is, I don't know, 150-ish? I don't know. Print out. Bring that to the class. It's free. You've already paid your tuition. Why do you spend like $5 more to buy that college grade note? Well, I don't know how much does it cost nowadays. It's your lunch money. You can use that for your lunch money. Print out the notes. It's given as a PDF. Why not doing that? I really want to know the reason if you're not printing out. Go to Notes A1. This is PDF. Print out. Go to library, print out. Both pages, single pages, I don't care. File up in your binder. Bring it in to the class. That's probably most efficient way of taking this lecture. Okay? Am I convincing you? If not, it's your decision, okay? This is your education. It's not my, I'm teaching. That's the only thing I can do. If you don't want to run, how can I do? I don't know. So please do that. This is my advice. Okay. You can print out everything. I don't know, 200 pages. And then if the library staff complains, use my name. Okay, because they know me. I've been here 20 some years. They know me. Well, if you have a problem with that, go talk to Dr. H. I paid the tuition, man. Not, I shouldn't use that language. Well, I paid the tuition already. It is my right to print out 250 pages in library printer, of course. Okay, so let's just move on today. Any question before we move on? Okay, so please keep it up. So this updates page is always fresh, and then you keep receiving email every time when I create new update entry. Then if you cannot keep it up, just click on the link on each email. Just jump right in and take a look at everything. Okay. So A3, Unit A3, what is it? So let's start Unit A3 today, governing equations of aerodynamics. Now, governing equations of aerodynamics comes from two sources. Can you guess those two? Two classes, maybe you took it in the past. Go ahead. You don't have to raise your hand. Go ahead. Fluids, thermodynamics. That's right. So those are the two classes entirely. Basically, you took it in the past, so there's no excuse. Hey, I didn't know. Yeah, right. Kind of section. Okay. You should have known those things. Now I'm going to make it specific applications to aerodynamics. That's what it is. There's nothing new here in this unit. Go ahead. There.
I'm currently enrolled in thermodynamics.
That's fine.
So,
That's fine.
okay, so I
Yeah,
don't-
so you're going to kind of compare as you go in thermodynamics, and then hopefully if aerodynamics moving too fast, it is going to kind of backtrack of you, okay, when you hit that point of the thermodynamics, now you instantly recognize saying, oh, professor, you're talking about calorically perfect ideal gas. And then your professor is ME professor and saying, I don't speak that language. Only aero people talk about that. That's actually a sign of very good professor who knows what he or she's talking about. If the professor's response is, huh? Let me know who the hell that is. I'm going to re-educate that person. Someone's grandpa used to be doing that, right? Right. Yeah, I was one of them. You cannot screw up, huh? I hope you're still living. Yeah. Okay, good. That means. By the way, should I introduce you? I mean, sure. He's Zach. His grandpa is former dean of engineering, Dr. Richard Feld. Now it's not a secret anymore. Sorry about that. And he is the one educated me to create this class, so I cannot go wrong, and then you cannot go wrong. Sorry about that. So governing equation, let's just take a look at one at a time. There are a few governing equations in fluid mechanics. Everything is based on this one principle, or a theorem. Somebody please help me. This theorem is a source of everything. Somebody say it.
Conservation pass.
Somebody is saying something? Yeah? Well, wrong answers are always welcome. I don't expect you right answers. Anyways. Well, go ahead.
I'm guessing something that has to do with gas and ideal gas. Reynolds.
Reynolds. Oh, you know that.
Yeah.
Reynolds transport. Reynolds transport theorem. So here's an important question. Reynolds transport theorem. This is the fluid mechanics. Okay. This is probably commonly chosen as a job interview question. Hey, spend some time, tell me everything you know about Reynolds transport theorem. If I'm happy about your answer, I give you a job. How do you handle that? This actually happened multiple times because I keep telling those HR people or Boeing saying, oh, ask this question, you know. It's going to surface how much the student knows or have no clue. When I was a first year PhD student, my professor at the University of Southern California asked this question, hey, welcome to our research lab. By the way, this is something I want you to look at it. Of course, this is something to do with Reynolds transport, but report back to me next week. That was my casual conversation day one of my PhD at the University of Southern California. I freaked to death because I had no clue what this person is talking about. Professor, I forgot. I was like, what the heck? Was it even an English or something? What was he talking about? Reynolds transport, never heard of it. That was me. I was a first year PhD student doing aerodynamics. It's very common. People just don't understand very basic foundation, just keep moving and moving and moving and moving, have no clue after they graduate. I was one of them. So I'm not going to blame you if you don't know the heck of Reynolds transport theorem, but let's just go back to fluid mechanics, because fluid mechanics is everything. Just 90% of fluid mechanics Reynolds transport theorem. And then everything is coming from here. That's what it is. Reynolds transport theorem is basically important concept, something called control volume. Have you ever heard of it? CV. In fluid mechanics, you did lots of control volume analysis. What is that, and why do you need that? Those are the real questions you're going to get when you try to get a job. Go ahead, try.
So you use control volume to see how much of material, whether that be mass, volume, whatever is going through a certain area, so you can determine its flow rates, and then you can
Mike,
analysis from it.
pretty good. Control volume is basically, sorry about that. Camera was on a weird angle. Sorry. This is the control volume. You know what I'm talking about? This is the control volume. Camera has certain area you can see.
It's like a snapshot.
That is control volume. Something gets in.
It only sees a certain part of.
That's right. On fixed volume in space. That's the control volume. Something gets in, could be mass, could be momentum, could be energy gets in. Something gets out. Something stays constant within or keeps changing. That's the difference between steady and unsteady. This is a control surface. Something gets in across this surface. This is a control surface. Something gets out across this control surface. This is a wall. This is a wall kind of thing. That's control volume. That's the tool. That's the tool to analyze flow field. Without that tool, it is usually impossible to analyze anything in flow field. That's why we choose that. In other words, something coming from control mass. Control mass is, what is control mass? CM. Control mass. What is control mass?
Like a
Fixed
mass.
mass, correct. Can you create the control mass of air? Well, I'm going to create this much volume of air right here, right now. I'm going to call this control mass. Okay? I don't know how big it is. I can make it as small as you can say. This is control mass. This control mass is creating flow field, start flowing like this, hitting the surface. It's not hitting the surface, but you can keep track of the motion of that control mass. What do you call that kind of pass? This is called pass line. A single particles passes pass line. Control mass is based off of one single item. You put your eye on one single item. It could be collection of particles making it this volume. This is control volume. I want control mass. In other words, 1 kilogram of mass creating this much volume. It's a control mass. It could be very, very small. I don't know. It could be a particle, but it's a single item. Now the single item moves along the path. Suppose if you want to analyze that kind of stuff, what kind of class you need to take? It's about dynamics. Dynamics. What is that class is all about? There's a one body in motion. Dynamics. This is one particle or one mass of air in motion. It's a dynamics. what kind of governing equation you're gonna get in dynamics class. That's why you hated that dynamics class so much. Differential equation. You have to always deal with differential equation because you fix your eye on a single thing. It could be super small thing, like a differential thing. So the equation comes up with a differential equation, right? So let me just put my story straight out. So this is a differential equation. So everything you deal with in control mass is differential equations, such as one-body dynamics. Classical sense, it's a dynamics. If you put your eye on a single air particle in motion, it's dynamics, essentially. It's not fluid at all. What makes that dynamics into the fluid dynamics? Well, you have to go through Reynolds transport theorem. In other words, lots of those particles are going in and out. You have to set a certain volume in space, then observe only in that area using this camera, maybe, I don't know. Camera field of view, that's the only thing I can analyze. Something gets in, this is the boundary, something gets out, this is boundary. I don't know how many particles flowing in, lots of things getting in. So it's impossible to keep track of single particle in the fluid mechanics because it's so many, it's so small. That's why Reynolds transport comes in. Going through Reynolds transport using control volume, what kind of equation you have to deal with? Integral equation. Okay. What happens if you integrate the differential equation? If you're lucky, you get algebraic equation. Here we go. Now engineers are ready. I can use this algebraic equation, plug that number, and get the number out. This is my tool. You can never do such a thing in differential equation. That's called governing equation. Somebody's governing equation. Engineer says, how can I use it? Well, you cannot use it. You have to integrate under certain condition. Then you get algebraic form of equation. Then I can plug in and get the number out. So that is a big picture before you even step right into Unit A3. That's what you did in fluid mechanics. And in a sense, in some also. Okay. So please understand basics. Lots of people just don't have any clue about those basics. Just keeps moving. It's not going to get you anywhere. Okay? The big stumbling block is probably this class, for those of you who didn't understand the basics. Right now, this is a big stumbling block. Maybe hit the wall. Next, very thick wall is your job interview. You can never go through that unless you understand fundamentals. And you can put that fundamental into your own words and explain to someone. You can never get the real job in engineering community, period. I can guarantee, put the money in the bank for that. So I guess you have to start facing a reality, hopefully starting from this AE301, and carry on, okay, before you graduate. So let's move on. So the first subject here, let's just talk about 3 important governing equations supposed to be in your fluid mechanics class covered. 3 things, give me that. 3 very important governing equations, 1, 2, 3.
Ideal gas.
Ideal gas is not quite, well, yeah. That's probably thermodynamics though, more. 1, 2, 3 in fluid mechanics.
Continuity equation?
Continuity comes from conservation of something.
Conservation of mass?
Conservation of mass. Now, quiz 0 problem 1A, 1B, and quiz 1A, 1B, those are all about conservation mass, okay? So in the tire, there's no B, conservation mass. So conservation mass is one of the governing equations coming straight from Reynolds transport. Reynolds transport is a generic form of equation. If you read property in Reynolds transport theorem equal to mass, now all of a sudden this is conservation mass equation, integral form. And then if you integrate under certain condition, you can get equation called continuity equation. Here we go. This is algebraic equation. You can plug in, get the results out. That's called continuity. Number 2.
Bernoulli.
Bernoulli is coming from somewhere else. What is it? Bernoulli Bernoulli is something you want because that's the only thing you can use. But
Is it from Euler?
Euler, oh, Bernoulli, Euler. Euler comes from where? What is that principle? Leads you to Euler. Of course, here is a Reynolds transport, gets you this, Euler, Bernoulli.
Conservation of energy.
Conservation of energy,
Momentum.
momentum. Conservation of linear momentum. Although I appreciate your wrong answers, don't worry about it. So what is conservation momentum? In a plain everyday language. Plain everyday language. Or maybe you can use equation. What is conservation momentum?
Just
F equal to ma. Do you know that? F equal to ma. That is the only equation you're going to get from dynamics. Dynamics is F equal to ma. I know that. Give me A for that class. Because F equal to ma comes in from lots of different forms. But F equal to ma is F equal to ma, Newton's second law of motion. That's the only thing dynamics covers. Okay? That is conservation of linear momentum. F equal to ma. So third governing equation in fluid mechanics. This is actually Newton's second law. Newton's second law.
Does it have to do with like temperature and heat?
I think so. What is it?
Conservation.
What
I was
is it?
gonna say heat, but
Conservation, kind of heat.
Energy.
Energy.
That's the first law.
Thermodynamics, first law. First law of thermal. Energy is conserved. That's called conservation of energy. So those are the three things we're going to be visit. Okay. Now, in aerodynamics, we are going to purposefully sort of limit this thing because this is not thermodynamics class. We're not going to spend too much time for this. This is kind of limited. So this is short-handed version. If you're taking thermodynamics right now, you're going to go much deeper. And if you already took thermodynamics, of course, I know that kind of thing. So stay focused. So step by step. So let's begin with continuity, which is conservation mass. Okay. Page 1. So you're looking at small, tiny chunk of air. Let's say if I give you 1 kilogram or 1 slug of mass of air right here, right now. Here we go. This is my present, my air, which is 1 slug. This is my 1 kilogram of air. Okay, I got it. Okay, I got it. This is 1 kilogram or 1 slug of air. Okay? How much volume do I have? Well, volume is V1. Mass is 1 kilogram or 1 slug. Okay? So you can say, hey, density is whatever the mass, which is 1 kilogram or 1 slug, divided by the volume you create out of it. That's density, isn't it? Question, right?
In this class, are we going to signify volume as a V with a strike through it?
Capital V comes with lots of different meanings.
True.
So, okay, good question. So if I say this, you know this is velocity.
Velocity vector.
Yeah. If I say capital V is a strike through, this is the volume.
Okay.
So it's just, yeah, it's a good question. So I just wanted to avoid confusion as much as I could. So anyways, so density is whatever the mass given 1 slug or 1 kilogram divided by the volume it's going to make. So this actually depends on the pressure, isn't it? If you're given 1 slug of air, if you go all the way to the higher altitude where the pressure goes down, the volume gets, oh, it's bigger and bigger and bigger. Okay? So density is not a very good property to keep track of such a thing. Instead, I want to pick up something else. What is that something else? We already talked about.
Mass.
Mass is fixed. It's a control mass. Yeah. So this is control mass. This, of course. Yeah, but it's not it. Yeah, thank you for wrong. Yeah. It's someone else. I don't want to deal with density, but something better we want to deal with.
Pressure.
To specify compressibility. Go ahead. Don't raise your hand. Just speak up. Speak, Stephen.
Mass flow rate?
No.
Specific density?
Specific something.
Specific
Specific volume is inverse of density. That's much better to visualize what's going to happen. I'm talking about compressibility. How much you can compress air in the flow field. Suppose this is 1 kilogram of air creating this much volume starts flowing and flowing faster and faster. What happens to pressure? Pressure drops.
Yes.
And the volume keeps getting bigger, 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 bigger. So how much volume do you get out of 1 kilogram mass? What is that property? That's called specific volume. Inverse of density. So specific volume is much sort of making sense if you use it to specify compressibility. So that specific volume change is so severe, you can never call that incompressible flow because expands and compressed within the flow field, that happens. Volume keeps changing as it grows. What happens to less than 0.3 Mach number is that change is so small, let's ignore it. That's called incompressible flow. Incompressible subsonic less than 0.3 Mach number, the Cessna 172, in maximum speed, still 0.3 or less. Now, suppose if you're talking about high-speed airplane in high altitude, cruising Mach 0.9 kind of ish, of course, this kind of thing happens all the time. As the piece of air flows around the airplane, expands, compress, happens all the time. Now, at that moment, as you can see, the volume change happens all the time for the 1 kilogram of air. Compressibility is something you can never ignore. Density changes. That is high-speed aero. Okay. So let's start from there. So we are going to define something called stream tube. This is a very similar or simplified model for the rocket nozzle. Stream tube is a tube created by streamline. Definition of streamline is across this streamline, velocity is always tangent, so there's no flow punching through the streamline. So this is idealized rocket nozzle, stream tube. Now suppose if you're given such a thing, this is inlet, this is outlet of a tube or something. Okay? So this is the property at the inlet, density is rho 1, cross section is A1, velocity is B1, velocity magnitude. Let's assume velocity magnitude is uniform across this cross section. That's called one-dimensional flow, right? In fluid mechanics. Do you remember that? Magnitude is uniform across this cross section. That's B1. Rho 2, A2, B2. That's property of section 2. What is the continuity equation? Somebody please tell me that.
It's also called, it's AB times
AB.
continuity.
Continuity equation, yeah. A1, B1 is equal to
A1, A2, B2.
A2, B2. No.
No.
Actually, this is okay as long as you satisfy something.
If the fluid has constant density.
You must have a constant density, rho 1 equal to rho 2. That's called incompressible flow. Now, the condition for such a thing L1 is Mach number less than 0.3 for both. Mach number here, both less than 0.3. That's the only condition you can have. Now, the homework programs start to come in Unit A3. Lots of times students making this classic mistake. Oh, let's examine the Mach number of this program. Mach number of this one is, oh, this is only 0.02. Let's use Bernoulli. Here we go. Now, how on earth you know the other side is also less than 0.3 Mach number? No one checks it. If you do such a thing, but I'm not going to give you any partial credit. The hell, this is wrong solution. Make sure you double check Mach number everywhere when you employ Bernoulli's equation. What am I talking about? Bernoulli's equation. Bernoulli's equation required something. But anyways, continuity principle basically says that you can define something called mass flow rate across control surface in, control surface out. If this is stream tube, single in, single out, mass flow rate in is equal to mass flow rate out is a continuity if it is steady flow. If it is not the steady flow, you can never even use this equation. Where is it? Okay. This is a continuity single input, single output. Density could be a variable. You can never say that. However, this is a steady flow. Then and only then you can get this equation. Now, if the density is constant, which is less than 0.3 Mach number, incompressible, rho 1 is rho 2, drops out. Then and only then, you can get this equation. A1B1 is equal to A2B2. So here's the important question. When you took fluid mechanics, did you go through that process? Starting all the way from original governing equation. This is the original governing equation of continuity. Did you start from here?
Yes.
Start from here, get this equation then. If I give you pop quiz right here, right now, can you do that? Start from here, get this equation. Apply this equation to this, get this equation. Can you do that? I don't want to hear you say no. That means you don't have a skill set. You don't have a prerequisite for this class. So let me do that. You can watch. Okay? So starting from here, well, which one do you want to use? These two are the same equation. This is the fluid mechanics, Manson-Yango-Kishi, Iowa State University, ME professor's equation. This is John D. Anderson, the god of aerodynamics, professor of University of Maryland, god of aerodynamics. Everybody uses his textbook in this country. This is aerodynamics version of continuity. This is fluid mechanics version of continuity. It's the same thing. Which one do you want to use?
Fluids.
Fluids. Yeah. So D. It's the same equation, okay? It's just a different look. Okay, so this is control volume. So this means this is a control volume over integral. So this is triple integral over the volume. It's the same meaning, right?
Yes.
Good. So read rho dB. So this B is a volume. This capital B is a volume for Anderson. This B is what Manson-Yango-Kishi. Okay, anyways. So this is integral over control surface rho times V dot N dA is equal to 0. Huh? So I'm going to apply this equation for the control volume you define. Let's define this as a control volume. What is control volume? It's a volume in space. This is a fixed control volume. Then as you define your control volume, you define the control surface. This is control surface. This is a control surface. This is a control surface 1. Control surface 2. You don't have to take any notes. I'm sorry. This is something you already went through. Just to look at it, try to understand it. You don't have to take any notes. Give me a break. If you don't get it, go back to fluids. So what's this? And what? Anybody? What's this? What's this? What's this N?
It's a unit normal vector.
Outward, unit normal. Outward, outward. Means from relative to the control volume, outward. And then unit, which is magnitude 1, normal, which is perpendicular to the surface. Good for you. Good for you, Zach. So this is outward unit normal for control surface 1 and 2. Now obviously each control surface, you have a velocity, right? Well, this is a velocity is a vector. B1 is incoming with a magnitude B1 uniform across the control surface, right? So this is a velocity B2 uniform across the control surface 2. If you take a dot product, what happens? Okay, this is density, right? Is this a steady state? Yeah, this is a steady state. If it's so, this is 0, steady state. What does it make steady state? If the mass within this flow field defined by control volume, if the mass within the control volume doesn't change over time, it's called the steady state flow. You can drop that term altogether. Now you have to deal with this term, right? So this term is integral control surface 1 rho 1 B1 dot N1 dA1 plus, because you have two control surfaces, control surface 2 rho 2 B2 dot N2 dA2. Those two added together equal to 0 because you have two control surfaces. Listen, don't take any notes. You don't have to. Just listen and take a look. and understand it. That's your skill. If you have to take a note right here, right now, you don't have a skill. Don't take any notes. Pay attention. That's what I want. You get that? Pay attention and understand. That's what I want. That's the real skill. You already took these notes when you took fluid mechanics, right? If you have to take a notes again, go back to fluid mechanics. Go ahead.
Is the velocity across the control surfaces an average velocity accounting for
Yeah.
no
It's basically,
fluctuation?
my assumption is the magnitude of velocity v1 is uniform, which is v1. Magnitude of velocity v2 is uniform, which is v2. That's the assumption, 1D flow assumption. Okay. You can, of course, introduce the variable. All of a sudden, you have to deal with real integral because it's an all of a sudden velocity function y. Okay. You can always make things more complicated easily. Okay, good. That's right. So let's finish up. What happens here? If you take rho 1 and then v1 n1 dot, what's v1 n1 dot? Anybody? Take a dot product. Go ahead.
Negative.
Negative. Negative. Negative what?
Negative
Negative.
direction. But
Yeah, it's a negative. Negative something.
scalar
What's-
Negative.
Negative. Negative v1. Magnitude gets out because you take a dot product of opposing vectors.
Right.
Multiply by rho 1 also because you integrate over a1. So this is minus rho 1 a1, isn't it?
Yes.
Right? Negative sign because you took a dot product for opposing vectors. How about this? Take a b2 dot n2, positive b2, and then rho 2 a2 comes in b2, rho 2 a2. This is positive. Set equal to 0. Here we go. You got this equation, right?
Yes.
Can you do this?
Yes.
That is the skill of fluid mechanics. So this equation didn't come or somebody will give you automatically in this class. You have to derive it. So from now on, okay, I'm not going to give you this equation. Okay, go ahead, plug and check. That's fluid mechanics. I'm not going to do that. So just about every moment, if you see the equation you need, you have to derive it from the original principle. Be ready for it. Nobody's going to give you this equation, hey, go ahead, plug and check. That thing is over in fluids. Not going to do it. That means there's only one way to pass this class. You understand it, get the real skill. You can't pretend. All right. Let's move on. Any question about continuity? So this is a quick review of continuity principle from fluid mechanics. Okay, obviously there's a constraint. If you're talking about roll speed here, wow, this is the roll speed. That means less than 0.3 Mach number, density change can be ignored. In other words, specific volume change can be ignored because it's so raw speed. The volume doesn't change much. Okay? So let's just move on next page. So simplification of continuity. Less than 0.3 incompressible flow. Okay? Now, do you remember less than 0.3 is something you can use Bernoulli's equation? You remember that?
Yes.
Bernoulli's equation has nothing to do with this discussion. Bernoulli's equation is coming from second governing equation, which is conservation of linear momentum. Okay? I'm still talking about conservation mass. All right? So conservation mass, surprisingly, giving you very simple information and very simple information only. Suppose if you design something like a tube or something, you want to have a speed, something you want to set here. How much cross-section do you need? That kind of information. Information is very limited. However, that kind of information is oftentimes required to be used against linear momentum equation. So that's what the conservation really is. Okay? So you're going to realize it, hopefully, as you start working on homework assignments in Unit A3. But here's a warning. If you don't understand the basics of fluid mechanics, now is the only time you can go back over and over and over again to your fluid mechanics notes, or it could be my fluid mechanics version of notes, which is pre-deposited for you. Okay? Make sure you understand those basics. You cannot move on having no clue. It is going to only hurt you as you move on. If you have no clue what you're talking about, you cannot move on. You can only pretend to move on. Okay, so make sure this week is important. I'm going to cover everything very, very, very slowly. Knowing that most of you don't have a skill set necessary from fluid mechanics. You have to build it. You are the only one who can build it. If you have a notes who already took it, go back, get it, read it again, go visit your professor asking questions, or go take a look at my notes, post it, do whatever it takes. Start all the way from quiz 0. Quiz 0 is the key. I hope you figure out everything in every detail. And then I'm going to give you a series of quizzes. Quiz 1, you're done. Quiz 2, you're working on it. Quiz 3 is coming up. Okay? Keep up. There's no time for you to take a rest if you don't have a skill. You get that? Get the real skill. That's the only way to survive in this class. I'm not kidding. Any questions? Have a good day. See you guys on Wednesday. Let me stop recording. Okay, 2 people online. Do you have any questions? I'm going to stop recording.